through all different types of applications that we can use for our derivatives. Our last type is tangent line approximations, which is also called linear approximations or linearization, and then also L'Hopital's rule. So, a linear approximation, as it said, is basically using the tangent line to approximate the function at an x value near a given point. So what happens is, if we're looking at a graph, so just some function, remember that. What does a tangent line to that graph look like? What does it mean to be a tangent line to the graph?
It only comes into contact with that graph at that one.
Correct. So like if this was my point, okay, my tangent line would just go through that one point. Yes? And we've talked about how to write the equations of tangent line. Okay, because the slope of the tangent line is the what? Derivative. And then we just need a point. So what we're going to do now is we're still going to be finding the equation of a tangent line. Okay? So we're going to say that this is at A. Okay, that x value is at A. Which means that what is that y value? It's a function. F of A and for the most part, we need to put a function. Yeah, but remember, all the notes are also there. So what we're going to do is, instead of saying, so like say I didn't want to know what the value of f of a was. I want to know some value, and again, it does have to be near a given point. So let's say that this is D, and B is pretty close to A, and for whatever reason, we can't actually find f of B very easily for our original function. So that would be right there. So the actual f of B would be here, okay? But what we're going to do is use L of B, okay? So L stands for linear approximation. So we're using that L of B as an approximation for our value. And this is helpful sometimes when like our original function isn't very nice to plug into, especially with like trig functions. Or if we have like really ugly functions, or if we just don't have a ton of information about our original function, but we do have a point and a derivative, we can still use it to approximate. So what is the equation of a line? Any line. So what equation have we been using to find the equation of a line? Yes, which is what? y1 minus
y2
equals okay. So we're going to let y1 just be y, okay? Same thing with x1, we're just going to let that be x, okay? Now, we said that the point that I'm wanting to use is my original orange point. So a comma f of a. So I have y minus f of a equals x minus a, because that's the x value that we're wanting to use there. So then what is our slope? Huh? Derivative, just the derivative? Specifically the derivative. How would I denote that? F prime of a. So our slope is going to be the derivative at a. And we write that linearization as L of x equals all of that stuff, and then we're just going to move f of a to the other side. And this is what we call our linear or tangent line approximation. Again, it's very similar to all of the steps that we've done in the past, it's just now we're putting like a different symbol on the front, element, instead of just leaving a y there. Yes, no, maybe? Let's look at an example. So it makes a little bit more sense once we start seeing some values. So it says find the tangent line approximation of the following function at the point 0x for f of x equals 1 plus sine of x, and then approximate x equals 0.1. Okay. So the first step that we need to find is that L of x, because then we're going to use our L of x to approximate 0.1. So again, what are the two things that we need in order to write the equation of a line?
Point and slope.
Okay, do we have a point?
Yes.
Yeah. So I have y minus, my point is 1, equals slope times x minus 0 in this case. How do we find our slope? What is the derivative of that? So the derivative of 1 is 0. Derivative of sine is, okay. And we are specifically wanting the derivative at our original a value. So this point, this x value is acting as my a value. So we're wanting to plug in what? 0. What is cosine of 0? One. So our slope is going to be 1. Agreed? So we say that our L of x equals x plus 1. Are we all okay with how we got L of x? Yes, no, maybe. So that's the first step. Yes. Correct. If it's a linear approximation, yes. Technically, you could do other types of approximations, but that is outside the scope of this. We will just do that later. Now, the whole point of that is, so notice we have our original function is sine of, or 1 plus sine of x. Usually we plug in like radians, right? Pi over 2, pi over 4, pi over 3 into a sine of x. Which means that if I was to plug in a 0.1 into sine of x, would I get a very nice pretty number? Not really. Which is why, like, if you didn't have a handy dandy calculator, or you were just wanting to try and calculate it quickly, plugging in 0.1 is not going to be super easy for that function. So what we're going to do instead is x plus 1 going to be a nice pretty number, or easy to calculate to plug into? Yes. So instead of trying to plug it into a sine, we're going to say, okay, we're going to approximate it instead using our linear approximation. And what do we get there? 1.3. And so we're saying that that is the approximate value of what we would get if we plugged 0.1 into 1 plus sine of x. Yes.
How did you get 0.12, or did you just get that?
I just gave it to you. I just didn't put it on the original. But again, that value does have to be something that is close to the original point. Because again, if you look back at like your previous page, notice that the farther away that this B value gets from my A value, the like worse my approximation is gonna be, depending on what your graph looks like. Does that make sense? Now for some graphs, near can be like a little bit farther, like 0.5 or maybe even 1. Usually we're not gonna go outside of a range of like 1 in either direction if you're using a linear approximation. Alright, now besides just plugging it into our calculator, okay, so yes, we could just plug in f of 0.1 into our calculator and get the actual value and then decide if it was an under or over estimate, okay? How else could we decide if that value is an under or an over estimate? If I cannot use a calculator and plug it into the original equation, how else would we decide if it's an under or an over estimate? Okay, what am I looking at for my graph? Kind of. Okay, so let's just graph it and see. So what does the graph of 1 plus sine of x look like? Not quite. There we go. Sine. Normally sine is what at 0? 0. So now we will have moved up 1. And then does sine start by increasing or decreasing after 0? Increasing. So do we all agree that it would look something like that? Yes? No, maybe. Okay. And let's say we are using, let's see, we're using the point at 0, 1 as our approximation line, yes? So that's gonna touch here and go up. Yes, no, maybe? Now, it's kind of hard to see since I didn't draw it super big, but if I were to plot the point 0.1, so pretending it's there, okay, is my orange line an over or an under approximation?
Over.
It's an over approximation. It's going to be an over estimate. We're okay with that. Now, on my original graph that I graphed on the other one, okay, so for like this one, is my green dot an over or an under estimate? Under. Okay. Would there be a way to decide if it was an over or an under estimate without even seeing the graph? Or is there a general rule that we can kind of come up with?
If it's like increasing the estimates, maybe it'll be another estimate.
So notice that this is increasing and that is increasing. You're on the right track. It is a characteristic about the graph that we want to look at. So your concavity is what's going to determine if it's an over or an under estimate. So notice that if our graph is concave down, okay, so like this one, it's going to be an over estimate. And if it is concave up, it's going to be an under estimate. So technically, they don't even have to give us the graph. What could they give us instead? They don't even technically have to give us the function. What information tells us the concavity of our original function? Second derivative. So as long as we have the sign SIGN, right, if it's positive or negative of our second derivative, then we can decide if it's going to be an under or an over estimate. Yes, no, maybe. Okay with that. What questions do we have there? Okay, let's look at one more. So it says selected values derivative of the function g are given in the table, it is known that g of 4 is 12. What is the approximation for g of 4.2 found using the line tangent to the graph of g at x equals 4? That's a lot of words. What is it asking us to do? What are some key words there that we should probably take away?
Approximation.
Okay, so we're looking at an approximation. So what's something else that we have used as an approximation? Not quite. So our derivative is the slope of the tangent line. What did we use to approximate the slope of the tangent line?
Over and oh my gosh, up and over, or like
So the
just
slope
looking at it.
of the
Maybe slope of 2 points.
yes, which is the what kind of line instead? Yeah, right. So we've also seen approximations, right? Approximate the derivative, or approximate the instantaneous rate of change, or approximate the slope of the tangent line using the average rate of change, or the slope of the secant line, right? So that's another place that we've seen approximations. But this time it specifically tells us to approximate using the tangent line. Yes. So that should be our first clue, is that we are wanting to write the equation of the tangent line. So what are the two things that we need to write the equation of a tangent line?
The point and the square.
Cool. Do they give us a point?
Yes.
What is it? 4 comma 12. Do they give us a slope? What is the slope of the tangent line? In general. What's the slope of the tangent line?
Derivative.
The derivative, yes? Do they give us the derivative?
Yes.
Yeah, do they give us the derivative at 4? Yeah, what is our derivative at 4? So do I have enough information to make a line? Yeah, so I have y minus 12 equals 2.2 times x minus 4. And again, we write our linear approximation by L of x and adding 12. Now, generally for your linear approximation, we're actually going to leave it in that form. Okay? The reason for that is, remember that I said the number that we plug in is always going to be pretty close to my original value, yes? So when we do this subtraction of x minus a, okay, it's going to give us a pretty small number. Now that subtraction is usually going to be pretty easy to do. So that's why we would go ahead and leave it. That's just a subtraction. So what are we trying to approximate this time? 4.2. So that is what we are plugging in. So what is 4.2 minus 4?
0.2. Yeah.
Yes. So we get 2.2 times 0.2. What is 2.2 times 0.2? No, you put that into your calculator. Huh?
0.4. So 1.2 times 0.2?
2.2?
It'd be 44 in the decimal.
Should be 0.44. Yes? Then what is our approximation there? 12.44. So in this case, we don't even know what our original function is. And we're still able to approximate. What questions do we have? say we have to have. Yeah, well, so like, I don't even have to have the actual second derivative. I just have to have information about the second derivative. Yeah. So like, let's so say all of that was the same, and I said like, and g double prime of x is greater than 0 for all x. Okay, so what does that tell us about our concatenate? It's greater than 0 because it's concave up, right? So it's concave up for all x's, yes? That means that my linear approximation is going to be an under x. Like I could still say and decide if it's a whatever. I do have to either give you the function that you can take the second derivative, the graph, or like that, information about the second derivative. Because I also could have just put in like another line of g double prime here and just given you some values of either positives or negatives, right? Because I would also tell if it's concave up or down. But there does have to be at least some information, but it doesn't necessarily have to be the actual function. Does that answer your question? Other questions on that? Alright, so we get to move on to L'Hôpital's rule. He's French. Well, there's technically like an accent over it. It's not La Hospital. L'Hôpital. So, L'Hôpital's rule is actually a rule. We're gonna throw it back a minute. It's a technique that we can use to evaluate limits. So, it's been a while since we've talked about limits. Okay? So good review over limits. But the reason why we don't use L'Hôpital's rule when we learn about limits originally is two reasons. One, to use L'Hôpital's rules, like I said, it's an application of a derivative, so you have to know how to take a derivative. So remember, when we first learned limits, we did not know what a derivative was yet. Okay? And then two, I'll show you on the next page, people tend to confuse L'Hôpital's rule with the quotient rule, and we don't want to do that. So that's why we wait a little bit to learn L'Hôpital's until we've like gotten our quotient rule down. But let's think back to our limits. Okay. What is the thing we always want to try first when we're doing a limit? Plugging in, direct substitution. Okay. Sometimes we run into issues though, and we get things that we can't evaluate, which are indeterminate forms. What do indeterminate forms look like? Not just a 0 on bottom.
0 over 0.
It has to be like 0 over 0. Because if it's a number over 0, remember that's going to go towards positive or negative infinity. Okay? But if I have 0 on top and bottom, that means we can't determine what that is. Okay? Are there any others? Okay. Any others? Okay. Those tend to be our main three. Alright? Technically, infinity plus or minus infinity is another one. We don't tend to see that one quite as often, but it is still an indeterminate form. Now, what are some of the methods that we've talked about up until this point besides direct substitution? So, like, if direct substitution fails, what were some of the methods that we used to find limits?
We would multiply 1 over a variable of the highest degree.
So that was when we were evaluating limits at infinity. So those weren't necessarily indeterminate forms.
Factor.
We did factor. What else?
We did a weird sign first time.
We did. We had some special trig rules. We had some in between there. We're missing a couple. Which is also called rationalizing. So remember that was when we had radicals. And then the last one was simplifying rationals. So remember where we found common denominators to simplify. Yes? Do we vaguely remember doing all of those things? Hopefully so. Again, all of that's just review. Because what's going to happen is, or like where L'Hopital's rule is going to come in handy, is in places where we can't do one of these things. Technically, if it's in indeterminate form, we can always use L'Hopital's rule. Okay? However, it's most powerful with functions that we can't do one of these. So, what L'Hopital's rule tells us is if the limit is in indeterminate form, then the limit as x approaches c of f of x divided by g of x is equal to the limit as x approaches c of f prime of x divided by g prime of x. Now that first part is important. It does have to be in indeterminate form, so we can't just use it willy-nilly because we feel like it. Okay? If we can direct substitute, then we need to do that first. The other big thing, which again I noted earlier, is that this is not our quotient rule. Okay? I am not trying to find a derivative here. What are we trying to find? A limit. So again, this is an application of a derivative. Okay? So I am using a derivative to find the limit. So your quotient rule still stands whenever I'm trying to take the derivative of stuff that has fractions. I can't just take the derivative of the top and the bottom when I'm trying to find a derivative. We all see the difference there. Which is why I hold off on showing it to you, because people tend to get those confused anyway, so I don't want to exacerbate the situation. Yes, no, maybe so. So let's look at it again. So let's look at this first one. I have the limit as x goes to 0 of e to the 2x minus 1 divided by x. So what do we always want to try first? Cool. What is e to the 0? 1 minus 1 is going to give us 0. So we get 0 over 0. Yes? And that is a indeterminate form. Agreed? Yes or maybe?
Yes.
Okay. Now, let's think about it. Can I factor that? Do I have any common things that I can factor out? Do I have a radical that we can rationalize? Do we have a fraction that we can combine? Or is that a special trig rule? Yep. So, e's especially are one of your instances where basically all of our other techniques don't really work. So besides just graphing it, it's kind of going to be one of the big places where we have to use L'Hopital's rule. So we're going to put equals. I'm going to put an LH over my equal sign to indicate that I am applying L'Hopital's rule. And then we need to take the derivative. So we are not evaluating that limit yet. Okay, so I still have to put our limit symbol. But I am going to be taking the derivative of the top and the bottom. So what is the derivative of e to the 2x?
Can be e to the 2x times 2.
Okay, so the derivative of e to stuff is just e to stuff. But if I have stuff other than just x and the exponent, we also have to multiply by the derivative of that stuff, or of the exponent. So the derivative of 2x is 2. So we end up with 2e to the 2x. What's the derivative of negative 1? 0. So we just end up with an e to the 2x on top. What's the derivative of x? 1. So now if we directly substitute, okay, e to the 0 is now 1 still. right? 2 times 1 is 2, divided by 1 just gives us 2. But kind of going back to what you were talking about earlier, Owen, is this also helps us on ones where we can't do the divided by, right? So like our dividing by x's stuff works when I have a polynomial divided by a polynomial, and we're trying to go towards infinity. But if I have something like a natural log of x, I can't just divide by an x in that case. Yes, no, maybe? Let's see if y'all can do better than second hour on this one. What does our graph of the natural log of x look like? That would be what your exponential graph looks like. There you go. So it has a vertical asymptote, yes? And is it increasing?
Yes.
Yeah. It's increasing slowly, agreed? So as x is going towards infinity, what is our y values going towards? Infinity, right? It's still increasing, so it's still going towards infinity. So this is still infinity, and then if I plug in, we can't really plug in infinity, but if we did, right, we would get infinity over infinity. Agreed? Which is one of our indeterminate forms. So another good review here. So I am applying L'Hopital's rule. So what is the derivative of the natural log of x?
1 over x.
1 over x. What's the derivative of x? 1. So I get the limit as x goes to infinity of 1 over x. And what is the limit as x goes to infinity of 1 over 0? So remember, as my denominator is getting infinitely big, our entire fraction is going to get infinitely close to 0. What questions do we have there? Okay. Because then our last type is still L'Hopital's rule, but it's given a table. It's our favorite kind, right? Yes, no, maybe? They're not going away. There will be tables and graphs on your test on Friday, on your final next week, and on the 18th. Why do you keep practicing that? Now, if I wanted to find that limit, what is the first thing that we want to try? Just like with any other limit. Direct substitution, yes? So, if I directly substitute, I have g of, well, what is 2 squared? 4. And 3 times 2 plus f of 2. Yes? Well, what is g of 4? So go to g, right, which is my third column, of 4. Yep, so I get a 0. What is 3 times 2? 6, right? Just 6. 3 times 2. And then our next one, f of 2 is negative 6. So what are we going to get? 0 over 0. So it is one of our indeterminate forms, which tells us that we can use what? L'Hopital's rule. Now, we do need to be careful, because what is the derivative of the top? So it's going to be g prime of x squared, but what do we also have to multiply by? 2x, because it is a chain rule. Derivative of the bottom, the derivative of 3x is just 3 times f prime of x. From there, we again want to try and substitute. Divided by the plus f prime of 2. So what is g prime of 4. 5. Times 2 times 2 gives us 4. And then we have 3 plus f prime of 2 gives us 7. So we get 20 over 10, which is also just, and that would be our answer.